Inductors in an AC circuit. Last time we talked about the response of a resistor to an AC voltage. Now we have the AC source connected across an inductor. So you can see here we can form a Kirchhoff voltage law loop and label this terminal plus, this is minus, this is plus, this is minus. So we have basically following the current, delta VL minus delta V is equal to 0. So the voltage across the inductor is L dIL dt minus delta V is equal to 0. So delta V is L dIL dt, which is delta V max sine omega t. So this here this is where we see the relationship between the current across the current flowing through the inductor and the voltage across the inductor. So if you isolate DIL, we have delta V max sine omega t dt over L, and by integrating this the right hand side, we can obtain delta V max over L integral sine omega t dt. That will become minus 1 over omega cosine omega t. So derivative of cosine is minus sine. So now we have a minus cosine omega t in the current and sine omega t in the voltage. So looking at sine omega t minus pi over 2, this is sine omega t cosine pi over 2 minus cosine omega t sine pi over 2. The first part is 0. So this is going to give us 0. And we have sine pi over 2 is 1. So this is minus cosine omega t. Therefore, I can see that this minus cosine omega t can be replaced with sine omega t minus pi over 2. So we can write the current flowing through the inductor as delta V max over omega L sine of omega t minus pi over 2. And here we observe the maximum value of the current as delta V max over omega L. So what is this telling us? Well, this is telling us that between the voltage across the inductor and the current flowing through the inductor, there is a phase relationship. The current is lagging behind the voltage by pi over 2. So this is minus pi over 2. So the current in an inductor lags behind the voltage across the inductor by 90 degrees, which is quarter of a cycle. Okay, so we have two important results. We have the maximum value of the current, delta V max over omega L, and the lagging of the current, the voltage across the inductor by 90 degrees. So if we plot the voltage across the inductor and the current flowing through the inductor, when the voltage is following the sine omega t pattern, you can see that I have the current lagging behind by pi over 2. So it's going to take a quarter of a cycle in order to reach 0 for the current. So this was already at 0 at t is equal to 0. This is going to happen at a quarter of a cycle, t over 4. And this is t over 2. And this is going to happen at 3t over 2. And that is the full cycle t. So you can see that the voltage is already 0 at the beginning. The current becomes 0 at time t over 4. And then the voltage becomes maximum at t over 4. The current becomes maximum at t over 2. So we have to wait another t over 2, a period over 4, in order to get there. So the current lags behind voltage by pi over 2. Okay, so if we plot the Phasor diagram for the voltage across the inductor and current through the inductor, the voltage phasor is a vector that has magnitude delta V max, and it's making an angle omega t in the counterclockwise direction with respect to x-axis, so that delta VL is delta V max sine omega t. This is the voltage. Now, the current lags behind the voltage by pi over 2, and we have to go in the negative direction. The positive direction is counterclockwise, so negative direction is clockwise. So we go 90 degrees in the clockwise direction. The current phasor has a maximum I max, which is delta V max over omega L, and it makes an angle omega t minus pi over 2 with respect to the x-axis. Okay. Now we define the inductive reactance x sub L as omega L. So this is basically to make it look similar to the resistance. In the case of resistor, we had I max equals delta V max over R. Now what replaces resistance in an inductor is this frequency dependent resistance, which is omega times L. So that's called inductive reactance. So our maximum current becomes delta V max over x sub L, and RMS current becomes delta V RMS over x sub L. And remember, I RMS is I max over square root 2, and delta V RMS is delta V max over square root 2. Now, the voltage across the inductor is L dIL dt. It is going to be so basically this is going in the opposite direction. We integrated it. Now we can take a derivative. So if you take the derivative, you will obtain an omega. Omegas will cancel, and then you will make the sine a cosine. Cosine omega t minus pi over 2. What is cosine omega t minus pi over 2? Cosine omega t cosine pi over 2. That is 0. Plus sine omega t sine pi over 2, that's sine omega t. So we recover I max times x sub L sine omega t. So remember that delta V max should be equal to omega L times I max. So that's what we obtained here. That is you can see we already obtained from the derivative an omega, so the omegas cancel, and we multiply it by L di dt, so L's cancel, so we obtain delta V max. So delta V max is I max times x sub L sine omega t. All right, so what we see from this frequency dependent resistance x sub L equals omega L is that an inductor acts like a short circuit at DC. When omega is equal to 0, zero frequency corresponds to zero resistance, so it's going to be a short circuit. It will act like an open circuit at very high frequency because omega L is going to be approaching infinity, so infinite resistance corresponds to open circuit. All right, so let's take a look at an example. In a purely inductive AC circuit, the inductance is 25 millihenries and the RMS voltage is 150 volts. Calculate the inductive reactance and RMS current in the circuit if the frequency is 60 Hz. The inductance L is 25.0 millihenries. The RMS voltage is 150 volts. The frequency is 60 Hz. And the inductive reactance x sub L is equal to omega times L, angular frequency times L, which is 2 pi times frequency 60 Hz times 25 times 10 to minus 3. So this gives us an inductive reactance x sub L of 9.42 ohms at this frequency. Now, the RMS current is basically the RMS voltage divided by the inductive reactance x sub L. So this will be equal to 150 volts divided by 9.42 ohms. So we will see that the RMS current that flows in the circuit will be equal to 15.9 amperes. All right. Now, let's continue with capacitance and then we can review these results. Now, if we replace this inductor with a capacitor, so we put a capacitor across the terminals of an AC source. Once again, we can form our KVL. You will see that if you follow this current here, it's going to be delta VC minus delta V is 0. Delta VC is delta V. Now, what is the voltage across a capacitor? It's the charge that is stored in the electrodes divided by the capacitance, Q over C. This must be equal to the AC source voltage, delta V max sine omega t. So the charge as a function of time, it oscillates in phase with the voltage, C delta V max sine omega t. However, the current that flows in the circuit is dq dt, so we have to take a derivative. The derivative will give us an omega and sine will turn into a cosine. So we have omega c delta V max cosine omega t. Now, what is the phase relationship between cosine omega t and sine omega t? Sine omega t plus pi over 2 is sine omega t cosine pi over 2, which is 0, plus cosine omega t sine pi over 2, which is cosine omega t. So cosine omega t can be replaced by sine omega t plus pi over 2. So we see that the current that flows in the circuit will be omega c delta V max, where cosine omega t is replaced by sine omega t plus pi over 2. And the maximum current we can read here is omega c times delta V max, or delta V max divided by 1 over omega c. So what is the phase relationship between the voltage across the capacitor and the current that flows through the capacitor? You can see that the current is leading the voltage by an angle pi over 2. So this is further in phase, so it's a higher phase. So the current is leading the voltage across the capacitor by 90 degrees. 90 degrees corresponds to, once again, quarter of a cycle. So if we plot the voltage and the current as a function of time, so this is our sine omega t, the voltage that starts with 0 phase, so we start from 0, and it's going to reach a maximum voltage at time t over 4. So this is going to happen at time a period divided by 4. So let's see what the current did. The current was already maximum at the beginning. Now at time t over 4, a quarter of a cycle, it is 0. If I wait quarter of a cycle, I see that the maximum voltage again follows the current. It's going to become 0, but then the current has become minus I max. So on and so forth. So we see that the current is leading the voltage. Now, when we plot the voltage and current phasors, once again we have delta V max, the magnitude of this vector, making an angle omega t with the positive x-axis in the counterclockwise direction, so that delta Vc is delta V max sine omega t. And then I have to add a positive angle, so I go furthermore counterclockwise. So I put another 90 degrees here, and my current phasor will have a magnitude, vector will have a magnitude I max, so it's going to be I max sine omega t plus pi over 2. That's going to be the basically projection onto the y-axis of this vector. So this is my phasor diagram for the capacitor. Now, analogous to delta V max over R, delta V max over omega L that we have seen for maximum current, here we have delta V max over 1 over omega C as the maximum current. Therefore, we define the capacitive reactance, a frequency-dependent resistance, as 1 over omega C for the capacitor. so that I max becomes delta V max over x sub c and I RMS becomes delta V RMS over x sub c. Now let's play with this a little bit. The current in the capacitor is C dVc dt. So delta Vc is basically delta V max sine omega t. So you can see that delta Vc will be the integral of 1 over C IC dt. So that's what we do here. The current I have found here. So if I integrate this, I'm going to get 1 over omega so this integral IC dt will give me a 1 over omega term. So these omegas will cancel. And then I have delta Vc is 1 over C integral I dt. So this C cancels and the sine will turn into a minus cosine omega t plus pi over 2, which is sine omega t. So I obtained the previous result and delta Vc is I max xc sine omega t. Okay, so for this frequency-dependent resistance, the capacitive reactance, 1 over omega c, what is the behavior for DC? When the angular frequency is 0, when this is 0, you will have 1 over 0, infinite, so that's going to be an open circuit. Remember, the inductor was a short circuit at omega is equal to 0, but the capacitor is an open circuit. And when omega becomes infinite, xc becomes 0, so the capacitor turns into a short circuit at very high frequencies. All right. Now, let's take a look at an example. A purely capacitive AC circuit. An 8 microfarad capacitor is connected to the terminals of a 60 Hz AC source whose RMS voltage is 150 volts. Find the capacitive reactance and the RMS current in the circuit. The capacitance C is 8 microfarads. The frequency is 60 Hz and the RMS voltage is 150 volts. The capacitive reactance is, as we have seen, 1 over omega c. It's a frequency-dependent resistance, which is related to the frequency 1 over 2 pi f c. So if I substitute the numbers here, it's going to be 1 over 2 pi 60 Hertz. The capacitance is 8 microfarads, 8 times 10 to minus 6. So this gives me a capacitive reactance x sub c of 332 ohms. And what is the RMS current? The RMS current is the RMS voltage divided by the capacitive reactance. So this is a purely capacitive circuit. So I have the RMS voltage 150 volts divided by 332 ohms, giving me an RMS current of 0.452 amperes. All right. So let's review what we said in this lecture. Having looked at the resistor in an AC circuit, we have seen that there is the current and voltage on a resistor are oscillating in phase. And we have seen that the maximum value of the current is maximum voltage divided by R. So this relationship we take as a reference and we look at what happens when I connect an inductor. Knowing that the voltage across an inductor is linked to the current flowing through the inductor as L dIL dt, with this KVL loop, I can figure out what the current is going to be, knowing that the voltage is delta V max sine omega t. So I integrate delta V max sine omega t dt, 1 over L gives me the change in the current delta IL, so it's going to be the current as a function of time. And then I can find the phase relationship by looking at this trigonometric identity. Sine omega t minus pi over 2 is minus cosine omega t, and I discovered that the current in an inductor lags the voltage across the inductor by 90 degrees. The inductive reactance is omega L, frequency dependent resistance, so that I max is delta V max over L, or I RMS is delta V RMS over X sub L. And this is the phasor diagram, where if I draw a voltage phasor like this, then I have to go in the clockwise direction 90 degrees to plot my current phasor. And from this frequency-dependent resistance, I have discovered that the inductor is a short at DC and open circuit at very high frequency. And here is a numerical example where we have used 25 millihenry inductance, 150 volts RMS voltage, and 60 Hertz. We can calculate the inductive reactance as omega L and I RMS as V RMS divided by X sub L. Now, if we replace the inductor with a capacitor, the voltage across the capacitor is linked to the charge that is stored. It's Q divided by C, or Q is equal to Vc. That is the voltage of the AC source, delta V max sine omega t, oscillatory voltage. The current is dq dt, so we obtain a cosine omega t. This time cosine omega t can be obtained from sine omega t by adding a phase of pi over 2, so we'll see that the current in a capacitor leads the voltage across the capacitor by 90 degrees, and furthermore we see that this frequency dependent resistance I max equals delta V max over X sub C is 1 over omega C. So when omega is equal to 0, we obtain an infinite resistance open circuit. When omega is infinite, it is short circuit. And when we plot the phasor diagram, the current is leading the voltage, so we have to go counterclockwise an additional 90 degrees with respect to the voltage phasor in order to plot the current phasor. And maximum current and RMS current are linked to the maximum voltage and RMS voltage, analogous to the resistor, where we replace the resistance by this frequency-dependent resistance, capacitive reactance, X sub C. And here's a numerical example where we have 8 microfarads capacitor connected to an AC source oscillating at 60 Hertz with 150 volts RMS voltage. We can calculate the capacitive reactance as 1 over omega C, where omega is 2 pi f, and I RMS as V RMS over XC. So you can see that the formulation for the resistor, capacitor, and inductor are the same. We have, the only difference is that the resistance is not a frequency-dependent resistance. We have frequency-dependent resistance, inductive reactance in an inductor, which is omega L, and 1 over omega C, capacitive reactance in a capacitor. And the other important difference between these two is that in a capacitor, the current leads voltage by 90 degrees. In an inductor, current lags voltage by 90 degrees. This is going to become very important when we put a capacitor, inductor, resistor together in an RLC circuit in order to figure out the overall behavior. Is it going to be more capacitive or more inductive behavior?